All right, so let's work on this problem. We're going to improve a little bit over the previous problem. We're going to try to find the influence line for the shear at C. So let's think a little bit about this. I'm going to cut my structure here at C. I'm going to find the shear internally there. Do you want to work the left side or the right side? You want to go left? That's okay with me. So if you go to the left side, you're going to need what? You're going to need the AY reaction. If you went to the right side, you would need BY. So before we even get started, I'm going to have to find the influence line for AY for my moving load, which we know can be anywhere up here. And I'll even do it at some position X. So let's find AY first. So how do I normally find AY for any kind of load? What would I do? Some moments about B. So let's do that. Let's sum moments about B, and let's say it's in equilibrium. So if this 1 is measured X from the left, then what is this distance here? 12 minus X. We've done that before, right? When we cut a structure and we're looking at shear force and bending moment functions. So now when I sum moments about B, this 1 is going to create a positive moment with a moment arm of 12 minus X. And my reaction AY is going to create what kind of moment about B? Negative. And it has a function AY, and the total distance is 12. So solve for AY, and you get 1 minus X over 12. So really that's the equation for the influence line of AY. Everybody see that? I can plot that. Maybe I should, just for you to see it. So let's plot that. At x equals 0, you get 1. And at x equals 12, you get 0. There's the influence line for AY. So you can see that when the load 1, the unit load, is at A, that creates the biggest reaction. And as it moves away, all the way to B, it has no reaction. But we don't want that. What do we want? Shear. The shear at C. And we've already decided that we're going to work the left-hand side. So I'm going to draw a free body diagram of that left-hand side. That was at 3 feet. But now I know AY, right? We solve for it. So this is going to be 1 minus X over 12. That's my reaction. And I'm going to assume that my unit load 1 at some distance X is there, and what I'm looking for is the shear at C. Here's my free body diagram. So since the unit load is operating in this range, this is the one where we're going to say that this is going to be valid from 0 to 3. So how do I find the shear at C? Some forces in the y direction. I'll assume up is positive. We'll make sure we're in equilibrium. What do we have? Well, we've got the shear acting down. We've got the unit load acting down. And we've got this reaction up. That'll be 1 minus X over 12. So when you solve for the shear at C, what do you get? Minus X over 12. And this is only good for 0 to 3 because when I'm on this body, which is only 3 feet long, this is accounting for my moving load being anywhere between 0 and A. The second case is when it's not. greater than that. In that case, would look like this. It's the same free body, right? My reaction at A is exactly the same because, see, it's got the function of x built in. Right? I still have my positive shear at C. And this is still 3 feet. But where's the unit load? It's moved. Right? So this is when the unit load is somewhere between 3 and 12. It's over here somewhere now. So when I cut it at C and look at the left-hand side, it's not there. Elvis has left the building. Is that too old a reference?
Got it.
You get it?
We got it.
So now what do we do? We sum forces in the y direction. So still, I have my shear at C down. I don't have another load here, but I have this one acting up. Plus 1 minus x over 12. So my shear at C for this one is equal to 1 minus x over 12. I just need to plot this. So now my influence line for the shear at C will look like this. So there's 3, there's 12. So, right, this is 3. I'll put a little mark there so you remember. There's 3 feet. This will be 12 feet. So from 0 to 3, what equation do I plot? This one. So when x is 0, I get 0. When x is 3, what do I get? I get minus 3 over 12, which is minus 1/4. And then from 3 to 12, what do I get? I use this equation. When x is equal to 3, you get 1 minus 3/12, which is positive 9/12, which is what? 3/4. And then you plot it all the way out to x equal 12, you get 0. It looks like that. Notice this. You see that change right there? What's the change in shear at C there? 1. What's the value of our unit load? 1. Will the change in shear always be 1? Yes. So where do I go to create the maximum shear at C?
C?
3 inches, but 3 feet, but to the right of 3 feet or to the left of 3 feet? Just to the right of 3 feet, it goes to 3/4. So think about you being a chunk of material in a beam that's part of a bridge, and a truck tire passes over your head. You feel your shear goes negative to 1/4 of the weight, and then instantaneously it passes over your head, it jumps to 3, and then decreases. So the shear force in the beam is doing this all the time, and that's what creates that vibration you feel if you're standing on a bridge and somebody comes flying by. The shear forces are changing constantly. So your structure looks static, but internally it is far from static. It is moving all the time. Very small amounts. You don't really see it, but it's moving. Again, I don't encourage you to do this, but if you ever get the opportunity to stand in the mid-span of a bridge deck as big trucks are flying by, it's kind of fun for a minute, and then it gets really scary. But it's amazing. Any questions about that?
Is this one of the instances where you're talking about being discontinuous?
Yeah, see it?
Yeah.
It jumps. But both sides are linear. And if you look carefully, what's the slope of this line? 1/12 negative. What's the slope of this line? It's exactly the same. These lines have the same slope. Pretty cool. Will they always be like that? No. Oh, I should stop. Any other questions? That took us 9 minutes with the discussion.